All right, so the last lesson in this chapter, and then again, quiz on Monday, is solving exponential equations. So we'll determine the solution of an exponential equation in which the bases are powers of one another. We'll solve problems that involve exponential growth or decay, as well as look at applications of exponential equations to loans, mortgages, and investments. So anytime something is either growing by a percentage or decreasing by a percentage, you can work with that by setting up an exponential equation for it, as well as, like we've seen, questions where something is doubling or tripling or being cut in half at regular intervals. So those are all different scenarios where we can actually use exponential equations to work with those scenarios. So again, an exponential equation is an equation that has a variable in the exponent. That's what an exponential function is, right? It's where you have the variable in the exponent. And then if you have an equal sign in there as well, that makes it an exponential equation. So at the top here, this is an example of an exponential equation. 2 to the x equals 8 to the x minus 1. You've got an equation because there's an equal sign there, and you have variables in the exponents. So exponential expressions can be written in different ways. It is often useful to rewrite the expression using a different base than the one that is given. This is really helpful when solving exponential equations because the exponents of the exponential expressions with the same base can be equated to each other. For example, if you wanted to solve that exponential equation, 4 to the 2x equals 8 to the x plus 1. You're trying to find the value or values of x that make that equation true so that the left side and the right side are equal. And this can be done, as it says there, by making the bases the same. You can express 4 as a power of 2 as well as 8 as a power of 2. So that's what this step here shows. Rewrite 4 as 2 squared and 8 as 2 cubed. And then when you have one exponent raised to another, you multiply the exponents and keep the bases the same. So that's what took us to that step right there. Multiply the exponents out and keep the bases the same. Now, this is an equation. The left side and the right side are equal to each other. If the bases are equal, then the other parts are equal as well. So that's how you can go from this statement or that equation down to that equation there. We are told that the two sides are equal. If the bases are equal, then the other parts have to be equal as well, meaning the exponents are equal. And so that's where that 4x equals 3x plus 3 comes from. There might be some bottles in there, though. Thank you.
You just put the bottles on here. There'll be a rest bottle. We're still shredding.
I'm good right now. Thanks. Okay, so that's where the solution comes from, right? And then remember, when you get an equation and you find a solution, it's always a good idea to check it, make sure it works, because sometimes you're going to get extraneous solutions, right? And on a diploma exam or on a unit exam, you have to do something to indicate when an answer is extraneous. So either you cross it out or you box the correct answer. To be safe, it's always a good idea to actually state this answer is extraneous, right? But you have to somehow deal with that part. So to start with, then we'll just do some practice rewriting an expression with a different power than what's given. And so for this first one, we want to write them as it says with a base of 3. 27 would be 3 cubed. What happened to you?
I went down the student's room.
Okay. You can grab your stuff and go. So 27 is 3 cubed as a base of 3. 9 squared, so you can write 9 with a base of 3. That's 3 squared, but because the 9 is squared, the 3 squared would also be squared. And when you have one exponent raised to another, you multiply the exponents and keep the base the same, so that would be 3 to the 4. Okay? C is obviously a bit more complex, but it's the same process. We can express 27 with a base of 3, that's 3 cubed. Because the 27 is raised to the 1/3, the 3 cubed would be as well. Also, the cube root of 81 squared could be written as 81 to the power 2/3. You might remember this. We learned about this in 10 can see that when you have a radical, it can be written as a power with a rational exponent. The denominator of the exponent tells you what root it is. So because it's a cube root, you have 3 as the denominator. The numerator of the exponent tells you what power it's raised to. So for this first part, this first factor, because factors are things that are multiplied together, you've got one exponent raised to another, so you'd multiply the exponents and keep the base the same. 3 times a third would be 3 over 3, or 1. But now 81 can be written with a base of 3. That's 3 to the 4th to the power 4 over 3. And you can multiply these exponents together. The 4 would be 4 over 1, because when you multiply fractions, it's top times top, bottom times bottom. So that would give us 3 to the 60 over 3. And now we are multiplying powers with the same base. The law says you add the exponents and keep the base the same. So I'd have to write this 1 with a base of 3 by saying it's 3 over 3 plus 16 over 3. And now we can add those and get 3 to the 19 over 3. So now we've rewritten that expression as a single power with a base of 3.
How did the 2 over 3 become 4 over 3?
That's a very good question. I have no idea. I probably had 4 in my brain from this 4 here, because I should not have done that. So that's 2 over 3. So this will be 8 over 3. When you multiply, and now it'll be 11 over 3 when you add 3 and 8. Thank you. All right. So now for these next ones, we want to write them with a base of 2. And we can do that because 4 is 2 squared. The 4 is raised to the power 3, so the 2 squared would be as well, and 2 times 3 is 6. Question B, 1 over 8. The 8 can be written as 2 cubed. And this really isn't a power of 2 right now, because it's 1 over a power of 2. So what we would do is move the 2 up to the top, which would change the exponent to negative. So now it's written as a power with a base of 2. 2 to the negative 3. And then for C, again, 8 is 2 cubed, which would be raised to the power 2 over 3. 16, the square root of 16 to the power 3. Well, a couple things you could do here. You can actually take the square root of 16, which is 4, and then that would be cubed. The square root of 16 is 4. And then you can express 4 as a power of 2. But first, I would multiply the exponents for this first factor. The 3's would cancel, and you'll get 2 squared times 4 is also 2 squared, which is raised to the power 3. So you'll have 2 squared times 2 to the 6th. And now you multiply them together by adding the exponents and keeping the base the same. And by the way, you can use a calculator to check all of these. So if we check the last one that we did, we can get a value for the original expression, and it should equal what we got for a simplified expression. 2 to the 8th, I think, is 256, I think. But wait for the calculator to fire up here, and we'll put the original expression in, see what we get, and it should equal what 2 to the power 8 equals. There we go. So 8 to the power 2 over 3 times the square root of 16 to the power 3. 256. And 2 to the power 8, the answer we got, has the same value. Right? So it checks. Okay? And we could have done that for the previous ones as well as the ones above. So we use this process to help us solve some exponential equations. If we can make the bases the same, then we can make the exponents equal, and that's how we solve them. If you can't make the bases the same, that's where logarithms are going to come in. Okay, I've said before that one of the uses of logarithms, it allows you to solve any exponential equation. Like these ones here, if you can't make the bases the same, then that's one of the things that we use logarithms for. But for this lesson, because we're solving exponential equations, we haven't learned about logarithms yet. These ones can be done by making the bases the same. We can express, and actually in this case, we can actually express both with a base of 4 because 64 is 4 to the power 3. The other option would be expressed both as a power of 2, which you could do. But if you recognize that 64 could be expressed as a power of 4, it makes it a little bit easier. So as we've seen, 64 is 4 cubed. So I would simplify the right side by multiplying the exponents. And now we have both sides expressed as a single power with the same base. The two sides are equal. If the bases are equal, the other parts, the exponents, are equal as well. And so now we need to solve for x. Subtracting the x from both sides, we'll get 2x on the right, and then divide by 2. X equals 1. There's our solution, which we will check. And you can check it in the calculator if you want, or in this case, when x equals 1, 1 plus 2 is 3, 4 cubed is 64. And when x equals 1 on the right side, you get 64 to the 1, which is 64. So it checks. Right? It checks. For question B, the only way we can express 8 as a power of 4 is if we use a rational exponent. It can be done, but you'd have to figure out what rational exponent, 4 to what power equals 8. So it's better to, in this case, write them both with a power of 2. 4 is 2 squared to the 2x. It equals 8, which is 2 cubed to the 2x minus 3. Before we can draw up the bases and say the exponents are equal, we have to first express both sides as a single power with the same base by multiplying out those exponents. Now we can say, because we have an equation, because the two sides are equal, if the bases are equal, the exponents will be equal as well. So if I add 9 and subtract 4x from both sides, and then divide by 2, x will equal 9 over 2, or 4.5. So if we check this, the original equation is 4 to the power 2 times x, which we found to be 4.5. Big number, 262, 144, but we should get the same thing on the other side. 8 to the power 2 times 4.5 minus 3. Same number. So our answer is correct. Okay, always a good idea to check these to make sure. Says solve and then check using graphing technology. So we'll look at that. In this case, we can express the right side with a base of 2 because 4 is 2 squared. Multiply out the exponents on that right side. And now we've got both sides expressed as a single power with the same base. The bases are equal, so we can say the exponents are equal as well. And then solve for x. Subtract 2x from both sides, divide by 2, and there's our answer, x equals 3. So, how do you check this on the graphing calculator? Well, we're saying that x equals 3 is a solution to this equation. It's a value of x that makes the left side and the right side equal. So,
Sorry to interrupt, but do you have paper?
I'm good, thank you.
Okay.
So this will be the value of x at the point of intersection of the two equations. So that's how we would check it on our calculator. Y1 would be the left equation, 2 to the power 4x. Y2 would be the right side, 4 to the power x plus 3. Zoom 6 to set our windows to the standard settings. And then find the point of intersection. Second function trace, number 5 for intersect. Enter, enter, enter. And the value of y is quite large, but that's not what we're looking at. We're looking at the x value, x equals 3. That confirms that that is our solution. Right? For question B, we could write both of those with a base of 3. 9 is 3 squared to the 4x, and that equals 27, which is 3 cubed to the x minus 1. So we'll get 3 to the 8x equals 3 to the 3x minus 3. So now we've expressed both sides as a single power with the same base, so the exponents will be equal as well. When you subtract 3x from both sides, you'll get 5x on the left equal negative 3 on the right. So x will be negative 3/5, which is exactly negative 0.6. Be okay to use a decimal there because it's an exact value. So that should be where our point of intersection is. The x value at the point of intersection should be at negative 0.6. So we can check that on our calculator. Starting with 9 to the power 4x as y1, and y2 is 27 to the power x minus 1. We graph them and find the point of intersection. Negative 0.6. Remember, you can take that x value in your calculator and turn it into a fraction. Because that's the last x value in our calculator, if you quit out of there and you go x enter, it brings it up, and then math enter enter turns it to a fraction. On the TI calculators, you can do that. Okay? So as I said, if you can't make the bases the same, if you want to find the exact answers, you have to use logarithms. But you can use your graphing calculator to get an approximate answer. You just have to round it. Okay? You just have to round it, because if the answer is integral or rational, then you could have solved it like we have been solving it. But when the bases aren't the same, right now we have no option but to use our graphing calculators. And so if you saw a question like this, it would tell you what to round it to. In this case, we're not, so we'll just round to the nearest hundredth. 2 to the power 2x is our first equation. That goes into y1, that's the left side. The right side will be 3 to the power x minus 1. So when you graph them, and then find the point of intersection. It certainly looks like it's going to be negative somewhere to the left of the y-axis, but the calculator will tell us. So it's negative 3.01, it looks like. No, 81. Actually 82, if I round to the nearest hundred. Negative 3.82. And we would use approximately equal here because we're rounding it. Okay. For question 2, same thing. We'd use our graphing calculator. So it's 2 to the power 2x minus 1 is our first equation. That will go into y1. The right side would be 6 to the power x plus 2 minus 1. So if we look at that second equation and think about it in terms of a transformation, it would be the graph of y equals 6 to the x, shifted 2 to the left and 1 down. That's an h value of -2 and a k value of -1. Yes, I did. That should be a 4, shouldn't it? Thank you. All right, so we graph it and find the point of intersection. So it looks like that number is 1.999454. Yep, so we'd have to round that to -2. If we round to 2 decimal places, it would become -2.00, or just -2. But that's an approximate because, again, it's being rounded. Okay. So again, once we get into chapter 8, we will see how we can solve these algebraically so we can get an exact answer using logarithms. But for now, we use our graphing calculator, so we are getting an approximate solution. Christina plans to buy a car. She has saved $5,000. The car she wants costs $5,900. How long would she need to invest her money into a term deposit that pays 6.12% per year, but compounded quarterly before she has enough to buy the car? So we're going to use the exponential function equation that you're given on the formula sheet, which is, again, y equals a times b to the power t over t. And so y is the amount at the end, which in this case we are told is $5,900. That's how much she needs to have at the end. We said that a is the initial amount as long as the graph hasn't been transformed at all vertically, and in this case it hasn't. So a would be the initial amount of 5,000. Remember that b is the growth factor. So it will be represented by how much the money is growing. And in this case, we are told that the term deposit pays 6.12% per year, but it's compounded quarterly, which is 4 times a year. So every quarter, the interest will be calculated. But it's not calculated on 6.12%, it's calculated on 1/4 of that. So to find out what B is in this case, we would change the percent to a decimal, which will be 0.0612, and we have to divide that by 4 to get the quarterly interest rate. Compounded quarterly means it's being compounded 4 times a year. So we can take our calculator to figure out what that is. 0.0612 divided by 4. So it's 0.0153. So that's what our B value is. However, we're actually going to add a 1 to that because, let me write this out here, 1.0153, because every quarter she's going to have 100% of what she had plus 0.0153 more. It's growing. So you're going to have what you had before, 100% of what you had before, and that's what the 1 represents, plus 0.0153 more. So that is our value of B. Now, T is the time, which in this case is what we're trying to find. Right? We're trying to find out how long will it take for that money to grow. So T is the time, which is what we are trying to find in this case. And the other thing is that P is the growth period. It happens 4 times a year, every quarter, which means every 3 months. Because it's compounded quarterly, that means 4 times a year. That's every 3 months. 12 months divided by 4 gives us every 3 months. So this is what we put in our calculator. Again, our equation is y equals a times b to the power t over p. We said y was 5,900. That's our final amount. A is our initial amount of 5,000. B, our growth factor, is 1.0153 to the power t over 3. And we want to solve for t. Now again, we could find it algebraically using logarithms once we learn how to use logarithms. For now, we would use our graphing calculator. That's what we would do. So my first equation will be the left side, just the 5,900. The second equation will be the right side, 5,000, bracket 1.0153 to the power. And the only variable we can use is x, so it'll be x over 3. We're going to have to change our windows here because that first equation, y equals 5,900, we have to have a y value of at least 5,900. So you can manually change the windows if you want. Make the y max, say, 6,000. And maybe we'll set our scale at 500. You can also choose zoom fit if you want, which maybe in this case might not have been a bad option because we can't see the point of intersection. Maybe if we go zoom 0 for zoom fit, that's where the calculator picks the windows. Maybe it'll show the point of intersection, and it actually doesn't. So that's fine. We'll just change our windows. We need to make our x max much larger. So let's change it to 50 and maybe change our scale to 10 on the x-axis. Remember, we need to see that point of intersection. Now we can. Second function trace, number 5 for intersect, enter, enter, enter. So the time is 32.701. And again, if I quit out of there and bring my x value in, or my t value, 32.701. But remember, this would be in months because our time was in months, our P, our growth period was in months. So this number will be in months as well, 32.701 months. And then if we divide that by 12, we'll get the years. Approximately 2.73 years. And because it happens every quarter, that means it would be every quarter year, every half year, or every 3/4 of a year. You'd have to round this up to 2.75 because the interest won't be calculated until you get to that 2.75 mark. So 2.75 years is what that would be. Okay? Whoops. Okay. Determine how long $1,000 needs to be invested into an account that earns 8.3% compounded semi-annually before it increases to $1,490. So again, we're going to use y equals a times b to the t over p, where again y is the final amount, which in this case is $14.90. A is the initial amount. The amount starting with, which is $1,000. B, remember, is the growth factor. The interest earns or is at 8.3% per year, but it's compounded semi-annually, which is twice a year. So it'll be 1 plus, remember that 1 represents 100%, plus the percentage, the semi-annual percentage rate, which we can found by taking the 8.3, turning it to a decimal, and dividing it by 2, because semi-annually is twice a year. So 0.083 divided by 2 is our semi-annual interest rate, 4.15% every 6 months. That's the semi-annual interest rate. So this will be 1.0415. That is our B value, our growth factor. T is our time. That's what we're trying to find. And P again is the growth period, which is how many months go by until the interest is calculated. Because it's semi-annually, that means every 6 months. Every 6 months the interest is calculated. So when we find our T value, once again, it will be in months. But first, we'll write our equation out. Y is 1,490, and that will equal 1,000 times 1.0415 to the power T over 6. And we will use our graphing calculator to find that solution. I'll choose Zoom Fit, Zoom 0. Let's see if it'll give us our point of intersection. I think it might, even though we can't see it. No, it doesn't. So we have to change our windows here. So again, we're going to have to make our X max larger, just a little bit larger, not a lot. So let's change that to 75, let's say. Now we can see it. If I remember correctly, it doesn't matter that you can't see the point of intersection as long as the X value is within the window. And it wasn't. If the Y value is not in the window where the point of intersection occurs, the calculator will still give you it. But not if the X value isn't. So that value is 58.84, and again, that's months. Because P is in months, T would be as well. And if we want to write that in years, again, we would divide by 12, which gives us 4.9 years, which would have to be rounded up to 5 because the interest is calculated semi-annually, which means every half year. So it's either going to be rounded to up to a 0.5 or rounded up to a whole. Even if this was 4.6, you'd still have to round it up to 5. because the interest would have been calculated at the 4.5 year mark, but then not again until the next 6 months is up. So in this case here, it would be 4.9 which has to be rounded up to 5 years. So they'd have a little bit more than the $14.90 they want, but at least they'd have that much. Okay? So that's it for this lesson. You can work on page 364, numbers 2 through 5 and 7. And I'm going to get you to hand this one in. So you want to do it on a separate piece of paper so that you can hand it in. Remember, you should be checking PowerSchool, and if you have assignments missing, that you get them done and handed in, right? So make sure you do that. And again, that's the end of this chapter. So Monday we'll write a quiz on it. We'll also be starting chapter 8 on logarithms. And then after that chapter will be your third unit exam. Okay? A little longer than this one.